the idea of this lecture is that I would like you to have an overview of what goes into current ideas of binary evolution, starting from main sequence stars and going through many stages that may lead to formation of compact objects or binary compact objects. So to start with organization details, we'll have 5 lectures, 5 tutorials, and for the tutorials I'd like to ask you to have your computers, laptops ready, because during the tutorials I'd like you to learn the several tools that may be used for investigating binary evolution scenarios, and to be able to verify, check if you read about a binary evolutionary scenario, if it's fine, if it's stupid, if it's good, if it's wrong, or what's good about it, what is uncertain about it, and to know what whether you should trust it or not. So this slide summarizes my goal for this next 5 days. I'd like you to get these little building blocks from which you can build evolutionary scenarios, and you can shuffle them for each particular case, and in the end you should be able to build some nice pyramids or nice towers, and on top of these towers you may have binary neutron stars or binary black holes, and you will know whether this construction of each tower, whether it's stable, unstable, or what kind of blocks are needed. But at least I'd like to equip you with a set of nice building blocks for constructing binary scenarios. There is a book on that is a, no, I'm not really basing these lectures on this book, but it's an excellent book to check on various processes, and you should use it as a reference for the binary evolution processes, and for verifying the ideas that I will be and expanding on the ideas that I will show to you. So, for today's course, for today's lecture on binary stars, I'd like to start with an observational introduction. So we know that there are binaries there, and they come in all sorts of shapes and sizes, and most of them we can see as two relatively unevolved low-mass stars orbiting around one another, and there is a number of ways that we can find out that a given object is a binary star and not a single star. So it appears that there is quite a lot of them, and that most of the stars, at least more than half of all the stars, exist in binaries. And because of that, it's not enough to know the evolution of single stars, but you have to take into account the binary interactions in order to realize, to find out what will the evolutionary, what will the stellar evolution lead to because of the presence of companions, and the binary stars are a very important ingredient. The binary stars are rather a rule than an exception. So so I understand that most of you are familiar with the single stellar evolution, and that you know something about the single stellar evolution. So I will briefly summarize the single stellar evolution later on, probably today, but and we'll do some single stellar evolution exercises during the tutorials, but I will not be doing any detailed investigation or teaching on the single stellar evolution. So we know that they are abundant. About 60% or so of stars are binaries, and even a small percent of stars is hierarchical, triple or multiple systems. So these systems are very important in order to understand the stellar population and the stellar the stellar evolution. So now the important thing about binaries is that if we want to measure the stars, if we want to find out what the properties of observed stars are, we would like to be able to measure their masses and radii and properties. And with single stars, we have a very limited amount of ways we can do it. With single stars, essentially, you look somewhere, you see a nice shiny point, but you want to know what is the radius of this point. Is it really a point, or is it a huge ball of gas? And how can you do that? So one thing is you can measure a spectrum. And if you have a spectrum, you can, you don't really have to measure the spectrum precisely to get the temperature. You can measure it in the brightness in a few bands and get a rough estimate of the spectrum, assuming that the radiation from a star is close to black body. If you do much more precise, measurement of the spectrum and look at spectral lines, you can estimate the surface gravity, and that's already one clue on the size and mass of a star, because the surface gravity is a function of mass and size of the star. You can get chemical composition, but in order to get the radius, what you really need to do is get the luminosity. So apart from spectrum, you can measure the flux, but flux by itself will not give you much information unless you have an estimate of the distance. So how to measure distances to stars? For nearby stars, what you can do is to measure the parallax, that is the annual motion of the star on the sky when the Earth moves around the sun. We look at the star at a slightly different direction, so it seems to be wobbling around its position in the sky, and from the amplitude of this wobbling, you can get the distance. So if you have the distance, and you combine the distance and the flux, you can get the luminosity, the absolute luminosity of a star. And if you have the temperature, you can get the radius, assuming that it's emitting as a black body, so you can get the size. So the accuracy of this, you see that there is a number of points that you have to go through. So the accuracy of these measurements is not that good, and in order to get the mass, once you have the size, you have to use the limited information about the surface gravity to infer the mass. So you see that for single stars, the amount of information that you can get is relatively limited. So here come the binary stars, and with binary stars there is much more many more things that you can measure. So with if you start with a binary, the easiest object to be recognized as a binary is the so-called visual binary. That is a binary for which you can see two objects, and if you observe it long enough, you see that these objects orbit around one another. So if a binary is relatively nearby, it has a long period. You can see see two stars, and you can see how they change positions and see their orbit. So what kind of parameters can you measure what kind of things can you measure for a visual binary? So any ideas? What would you say that we can measure? Period of rotation. Yeah. So one thing, yeah, we see one period. We see the. Okay. Anything else we can measure? We can see the size in the sky of the orbit. So that gives you the angular size of the binary. Yeah. Can we infer anything about the ellipticity of the orbit or inclination, the angle at which the orbit plane lies relative to us? Would you say that it's possible to find the inclination or not? Yes, okay. Everybody agrees? So here we have the visual binaries. So these are long period or nearby binaries. We can measure the period, the ellipticity, we can measure the inclination, the angular size, which is the size of the orbit divided by the distance.
Between ellipticity, eccentricity, and inclined intersecular orbit?
That's a very good question. So, because if you think about the motion, the angular velocity as a function of time, of the position on the orbit, it will be two different things. So if you have an elliptical orbit in the plane, you will have a varying velocity on the orbit, and if you have it inclined, a circular orbit that is inclined, your velocity will be different, the angular velocity. So also you can use this information to infer the total mass of the binary, yeah? Because if you use the Kepler's law, 2 pi over p squared, and if you divide it by d to the third, you get this. So you measure the angular size, you measure the period, and if you get the distance from the parallax, you can also have the total mass. Can you find the mass ratio in a visual binary? If you see two stars and you see orbits of two stars, then you see where is the center of mass, you know what are the relative distances, so you also know the mass ratio, and even the total mass and the mass ratio, you should be able to just find the masses from this information. So that's to show you that observing binaries can give you much more information by analysis. So this is an example of a visual binary with the period of 21 years, ellipticity of 0.15, angular size and inclination, and but with such a period you have to wait for quite a long time to really get a good grip of what's happening. This is Sirius with its white dwarf companion, and this is another example of a visual binary. So the visual binaries are not that common. There is not a lot of them. For the visual binaries, we have the binaries where we sometimes don't see a companion and we just see the oscillations of the motion of a binary around its proper motion, so it has some velocity in the sky, its proper motion, and if you see this, that the star oscillates around its proper motion direction, then it indicates that there is a companion, and actually you have an orbital motion around a center of mass point. Then there are common proper motion stars, which are stars with periods that are much longer than the typical observation time, so in excess of 100 or 200 years, but they lie close in the sky and they have the same proper motion, so we believe that they are very likely to be members of binaries, but we don't have the periods and we only think that they are there. Here is a list of the proper motion of the visual binaries that are known. There is not a lot of them, but since we have Gaia satellite that provides very precise parallax and proper motion measurements of millions and millions of stars, this list will probably increase in the next years. So the next group of observation comes from so-called spectroscopic binaries. These are the binaries for which we can measure the motion of the, well, we can see the two spectra of the stars in so we see some lines, and we can see that there is a part of a spectrum that comes from one component and another part that comes from another component. For example, there is one component with a very high temperature, say 50,000 K, and another which is cooler with a temperature of a few thousand K. So you see two black body spectra, and if you see spectral lines, you can also see the motion of the stars, because the spectral lines will move as a function of time. You cannot resolve the stars, they are seen as one source of light, but in the spectra you see the evidence of binarity. So if you see have a spectroscopic binary and you see the motion of the stars, what can you measure with something like that? Of course, you can measure the period. Yeah, that's easy. But what else? You can measure the amplitude of the velocity. Yeah? So this is the velocity along the line of sight, and it depends on the inclination of the system. So if the system lies in the plane perpendicular to us, you will see no variation. If it lies in the plane along the line of sight, then the variation will be very, very high. Can you see the? Do you think that you can measure the ellipticity of the orbit? Yes? How? Because if you see the variation of the velocity as a function of time, for the circular orbit it will be sinusoidal, and for an elliptical orbit it is going to deviate from sinusoid. So this will give you the information about the ellipticity. So we have the period, we have the radial velocity amplitude, and we have the ellipticity. We don't have the inclination. And there is a subcategory of these are binaries with pulsars, where the role of the spectral information is taken by the pulsar timing, and they provide you, this is a very important subclass, and that they provide you lots and lots of really relevant information. Here is an example of spectra of such an object. So you see, this is a spectrum, you see some, this is the typical spectrum of a companion star in such a system, like this one, and here you have some excess of emission that is probably a white dwarf companion. So that's the typical example of a spectroscopic binary. Now, what can you do with the information like that? What can you do with the radial velocity, amplitude, period, and ellipticity? It appears that after a very simple piece of math, you can derive something like the mass function. Are you familiar with what the mass function is, or is it the first time you see something like that? The first time, yes. Okay, so okay, I will not be deriving this now. We can do it later in the tutorial. But generally, if you have the observer here, this is the velocity, and you see the velocity moving changing as a function of the time. This is the period, time, and velocity. This is the velocity amplitude. You can it's an easy exercise in binary motion that you can calculate a function that is called the mass function, which relates the amplitude of the velocity of star 1 with the period and the ellipticity. So these are all the values that we can measure, and they can be related to the masses and the inclination of the system. And you can easily see that okay, if we have that this is F1, that this is smaller than m2 to the third by m1 squared and smaller than m2. So F1 is the lower limit on the companion mass. And this is important when we see binaries, for example, that contain a compact object and a star. You see the motion of the companion star, and from this you can get a lower limit on the mass of the companion. And if this lower limit is above 3 solar masses, and we know that the companion is a compact object, we see X-ray emission, we see there is a trace of accretion disk, then there is quite high probability that the companion is a black hole. So this is a very important measure of the properties of binaries, for which we see the spectroscopic, we have the spectroscopic information. Now, can we determine the masses of the individual objects with some precision when we just have this measurement? We can, if we have this, we can actually average it over all the possible inclinations, and we know that not all the inclination angles are allowed, yeah? Because if the inclination is close to 0, then we will not this binary will not be identified as a spectroscopic binary, because there will be no no motion along the line of sight. So the number of angles that we have is not completely this is not all the angles on the sphere. So for the in order to average it, we have to do the following. Okay, if F1 how does it go? Q is equal to M2 over M1. So M2 would be F1 1 plus Q squared times 1 over sinus I to the third, and the average value will be, if we average this, and it comes up to be about 1.25 F1 1 plus Q squared. And also M1 in this sense can be M1 will be 1 over Q, depending on this, how we define it. Yeah? Okay, so I should. If we define Q like this, then it's like that. Squared times 1.25. So, but this is an estimate of the mass that is quite uncertain, and it's not a very good way. Now, if double spectroscopic binaries, so that if we see the variation of the line velocity in from the two components, we have then two mass functions, and because we have two mass functions, we can take the ratio of the two mass functions, which will give us the mass ratio. If we take F1 over F2, it's going to be M2 over M1 to the third. So that's an additional information. We have the mass ratio, we have two mass functions, but without the inclination, we are not having the total mass. So if it's a visual binary, then we also have the inclination and the distance, and the system is completely solved, because when we have the inclination, we can, and we have the two mass functions, we can solve for two masses. And if we have two masses and the period, and we can have the size of the orbit from the Kepler's law, and if we have the size of the orbit from the Kepler's law and we have the angular size of the binary, we have the distance. So that way, if we have a doubly spectroscopic binaries and a visual binary, then they can serve as a distance probe and an independent distance estimate from that doesn't depend on the parallax. So.
Previous single binary, how do you get the mass ratio?
For the singly spectroscopic binary, you get the mass ratio when you. No, for the single spectroscopic binary, you don't get the mass ratio. Okay, so here is an example of the light curves of the velocity amplitude for an X-ray binary Vela X1, and you see there is an eclipse, and then you see nearly sinusoidal variation of the. Okay, this is the time delay, and this is the velocity of the companion star, which corresponds to a small ellipticity of 0.12. So this is a typical way you do it. Now, for the pulsars, we have lots of for the binaries with pulsars. We know that a pulsar is an object that emits this regular radio pulses, these are objects that are excellent for chronometry. For pulsar timing, and the pulsar timing provides us with the information on how the orbit around the pulsar is, what is the velocity. We can get the velocity of the orbit, we can get the shape of the orbit from the time delays, but there are also the general relativistic effects like periastron shift due to GR effects, the gamma parameter, which is the Doppler and gravitational redshift. There is Shapiro delay, which is due to the fact that the pulses from the pulsar have to pass through the potential well of the companion, and that introduces additional delay for the pulses when the pulsar is farther away than the star. So the system is essentially over. If we can measure all of these effects, we can measure many more quantities than there are variables in describe the system. So the system is essentially over determined, and we can get a full solution of the orbital motion, and we can get the extremely precise masses, especially in the case of binary pulsar systems. So because the system has too many more observables than parameters, this also provides this is also a case for verifying general relativity in the regime of weak fields, and you probably heard times about the constraints on GR from observations of binary pulsars, and how GR is really precisely consistent with the observations of the binary pulsars. Now, an additional group of binaries are the photometric binaries, which are the binaries for which we see variation in the amount that comes from the binary. So this variation in the amount of light can come from a number of factors. One is that we can have eclipses, like in this case shown here. So if you go along the time, sometimes one star is behind the other, and then we see less light because there is, the light is shadowed by the other star. Another variation that you can see here is that if the stars are close to one another, they will be tidally distorted, and because of being tidally distorted, they are not spherical anymore. And at any given moment, you see the projection of the shape of the star onto the direction to the observer, and therefore you have this variations of the shape of the light curve because you just see different amounts of area of the star, and at a given wavelength, you will also see different variation, because if the star is distorted, then the temperature on the surface of the star is not going to be uniform, and at different times you will see different variation, because the different parts of the star have the maximum of their emissivity at different wavelengths. So this is an example of such a star. So what are the quantities that you can measure when you have a binary that is a photometric binary and an eclipsing photometric binary? Certainly you can measure the period, yeah? Can you say anything about the relative sizes of the star? Yeah? So you can measure the width of the eclipse will be proportional to the ratio between the radius of the star to the size of the orbit. Yeah? So this is an important thing, that you should be able to measure the relative size of the eclipsing stars. And of course, I think for the eclipsing binaries, it goes without saying that you have a pretty good idea what the inclination of the system is. Yeah? If you see eclipses, it's in the plane, it's close to 90 degrees. So here is another example of a photometric binary where you can see, here the eclipses are really smooth, and only here you see some flattening of the light curve, and the stars are relatively nearby. But there are also examples like that where you have a giant and a compact object, or a star and a compact object, and in the visual you just see the slight distortion of the shape of the companion star, which in this case, is not really filling the Roche lobe. So your light curve will look like that, and you don't see really the eclipses. If you start seeing the emission from the companion, which will be very hot, so it's going to be not in the V band, not in the visual, but somewhere maybe in UV or X-ray band, you will see eclipses in the X-ray band. And you can also have extreme examples like that, where you see two stars that are relatively far away, and you see very deep eclipses when they pass in front of one another. So these are the photometric binaries, and for photometric binaries, you see the main thing are eclipses, deformations. You may have disks around the stars, and I'll show you an example of a light curve of a system with the deformations of the disk. So you can measure the period, the inclination, the relative sizes of the stars, and you can also measure the ellipticity. How can you measure the ellipticity? Or maybe I'm lying. Maybe you don't know what the ellipticity will be. So for a circular orbit, you will see two eclipses that are equally spaced. Yeah? For an elliptic orbit, the spacing between eclipsing of one star and by the first star by second star and the second star by the first star are not going to be equally spaced. So from the spacing of the eclipses, from the timing of the eclipses, you can get constraints on the ellipticity. So this is important. And yeah, if you do spectroscopy, you can do component temperatures, but let's go farther. So when you look at the slide curves, to me, a really impressive example of modeling a light curve is this one. This is Z camelopardi. So this is the light curve that people observe. And I think, you know, it always has impressed me how you can go from a light curve like that to a complicated model like that with so many pieces that fit the physical information we have. And you see a star that is distorted, it has different temperatures, there is an accretion disk that is eclipsed, there is a hot spot on the accretion disk where the accreted matter hits the disk, and this hot spot is also eclipsed, which you see here. So I think you know, it takes quite a lot of thinking to come up with a model like that from a light curve like that. People may not believe if it's true, and I'm not sure if it's true, but it is relatively impressive. So now let me go to what I would call the queens of the binary observations, which are double spectroscopic eclipsing binaries. These are very rare objects because you have to have spectroscopy of both stars. The inclination has to be 90 degrees so that they are eclipsing, but looking for them is extremely rewarding in the binary observing and a binary evolution group. So if they are eclipsing, then the inclination is close to 90%. If they are spectroscopic, we see two radial velocity amplitudes, and therefore we have the two mass functions. Yeah? So we have two mass functions, we have the inclinations, so we have the masses. Now, if they are spectroscopic, we can determine their temperatures, and this is one thing. And because you know we can certainly find their period, ellipticity, and inclination. So having the masses, ellipticity, well, the size of the orbit, yeah, just from the Kepler's law. Now, because they are eclipsing, you have the ratio of the size of each star to its to the size of the orbit, which gives you the sizes of the radii of the two stars. So now you have the fluxes, temperatures, and the radii of two stars, and from this you can calculate their absolute luminosities. Yeah, and so you have the flux and you have the absolute luminosity, and that gives you an independent distance determination. So these types of binaries are used for accurate distance determination, for example, to the Large Magellanic Cloud, which is essential in establishing the distance scale of the universe, and establishing the distance to LC is essential to establishing the age of the universe and all the cosmology. There is this distance ladder and distance to LMC that is mainly found by observing these types of binaries is a very important step up this ladder. So these are the systems on which quite a lot of cosmology relies. And apart from this, from the independent distance determination, they provide an independent determination of the radii and masses of stars. So they are very important for verifying the stellar evolutionary scenarios, because if we have, these are the main type of binary stars for which we can observe and we can measure both the masses and the radii, which we cannot really do for the single stars and for other stars in binaries. These are what I call the queens of the binary observations. Now, once we have all of these, we can observe deviations of behavior of binaries from the periodicity. So we have some slow period changes and observed with minus theoretical diagrams, and the periodicity can differ from being constant due to various factors. One is that there are winds, and if there are the winds and mass loss from a binary is slow, then in the times of on the time scale of say 10 years, which can be several tens of periods, we can see small changes in the orbit due to the mass loss from the system. We can have the presence of third bodies. So if we observe a binary, but it's actually a hierarchical system with a third star far away, but not very far away, the two stars are not are essentially moving in a non-uniform gravitational potential of the third companion, and that affects their periods, their motion, and we also can have some non-Keplerian potentials. If we have disks, then the potential will not be like 1 over r squared, and that can be also a reason for deviations of the periodicity. I have mentioned that there are also multiple binaries, triples and quadruples, hierarchical binaries, and that the statistics of the binaries is such that we have roughly 30% of the objects in the sky are single stars, 60% of the objects are binary stars, and 10% are triples and multiples. It should be binaries. Okay, you will see later on that within the binaries, all the binaries with the periods of less than 5 to 10 years will undergo some mass transfers in their history. So for quite a large fraction of this part of 60% of the binaries, the mass transfers are inevitable, and they will certainly happen. So let me now switch to this. So when we talk about binaries and the number of binaries, we want to know what is the statistics of binaries and what are their mass distributions, what are their parameters that, what is the typical masses, what are the typical masses of the stars, what is their mass ratio. So do you know for single stars what is the typical, no, what is the distribution of masses of stars that start at zero-age main sequence? Okay, that has been measured by looking at populations of young stars, and it is measured as there is a mass function that the m that is relatively flat for low masses, and then it falls off as a power law that goes to minus 2.3 to 2.7. So for the single mass stars, the initial mass function, it's called the IMF, is very steeply falling. This is about 1 solar mass, and then this is 0.08 solar mass. And then it goes down very quickly. So there is much higher mass stars than the low mass stars. For the binaries, it appears that the masses of the two stars are not really following the same distribution. So you can say that the mass of the primary is roughly distributed as the same, with the same distribution as the masses of the single stars, but the mass of the secondary, the initially lower mass star, is not coming from the same distribution, because if it came, we would probably almost see no massive binaries, because for an initial massive binary, a chance to get a equally massive companion would be extremely small, but that the number of binaries that a good parameter that describes the mass of the secondary is the mass ratio, and the mass ratio is somehow between 0 plus minus 1. Is that the distribution of mass ratios is close to uniform, so you can, once you have a binary with quite large initial mass, the chances for the probability distribution for the mass of the secondary is uniform between the lowest mass and the mass of this binary. Now, for the orbital parameters, we see binaries at all sorts of binary periods, and the orbital, so the lowest, the initial orbital period is determined by the size of the stars. So if they are too close, they will merge, or they will start exchanging mass even before they become stars. And then the highest end, it's very difficult to say, because we do not observe, it's very difficult to observe stars with, or binaries with periods in excess of 100 years. Yeah? Just for the fact that we are not observing the sky in detail for such a long time. And also it's very difficult to determine that these two stars are a binary over such a period. But in the region between this, say, few days or a few hours and 100 years, the distribution of initial periods of binaries, the distribution of periods or the orbital separations, is proportional to 1 over p, or in other words, the n over the a is roughly 1 over A, which means that they are equally spaced per logarithm interval of period or interval of the orbital size. So that's the initial mass function for the single stars, which is very quickly falling for high masses, and then for the orbits, this is the number. That's from a relatively old paper where we see that the number of stars per unit logarithmic interval is varying slowly as a function of the period. And the point why there are such a few numbers here is that there are lots of selection effects, and with these investigations, one has to look only for the very young stars before they were able to change their orbits due to winds, due to binary interactions or things like that. For the ellipticity, here is the diagram where we plot the logarithm of the orbital period for binaries versus their ellipticity. And you can initially see that there is an absence of stars with small periods and high ellipticities. But this is a selection effect, because for very short periods we have very quick, strong tidal interactions that leads to quick circularization of. So even if you take a sample of very young stars, there will be the stars from here migrate to low ellipticities very quickly. And if you look here, the distribution of ellipticities look relatively uniform, and it is agreed that the distribution of the ellipticities goes somewhere between e to 0 to 1, probably to there is more of the more elliptical binaries initially. Okay, so this is about the initial distribution of binaries, and now in the remaining less than half an hour that I have, I'd like to do a quick reminder course of the single stellar evolution. So if you have, you probably have studied in some detail the single stellar evolution, and are you familiar with this type of diagram, which is the HR diagram for the stellar evolution? That's a typical thing that the astronomers show. So on the axis we have the temperature of the surface on the surface of a star. On this axis we have the luminosity. As many things in astronomy, the temperature is plotted backwards. So this is low temperature, this is high temperature, and this is of course for historical reasons. And the lines that you see here show the evolutionary tracks of stars in these coordinates. So this line corresponds to very young stars early on the zero-age main sequence, where they start their evolution. And this diagram, you can also infer what is the evolution of the radii of the stars. Yeah? Because the quantity, we have the relation that the luminosity is the surface and sigma t to the 4th. Yeah? So if we have the temperature and the luminosity, we can infer the radius of the star, seeing this information. So what is happening here is that the stars move to the and up, never cross this line, which corresponds to about 3,000 degrees, and there is a very good physical reason for that, that I may mention in a moment. And so what is happening to the radii of the star as they evolve? The luminosity goes up, and the temperature becomes lower. So, for example, let's say that these lines are horizontal. So the luminosity is constant. The temperature becomes lower. So if the temperature becomes lower, the radii have to expand. So, and of course, there are interesting physical reasons coming from what happens inside a star, why their radii grow. But the main point here is that typically during the evolution of the star, except for short breaks like this one or that one, the stellar radii increase. And if they increase, so that means that if you start with a binary system and the radii increase, then one of the stars will sooner or later be able to fill its Roche lobe, and I'll talk about the Roche lobes later, and start transferring the mass, if the orbit is not too large. Now, by what factor can the radii expand? So the temperature, for example, let's say the case of a one solar mass star. It's a nice example. Say the temperature goes down by half an order of magnitude. The luminosity goes up by 4 orders of magnitude. So we can do the scaling here. R is equal to L over 4 pi sigma 10 to the 4th, and that's in a half hour, so that scales as L to 1/2 divided by T squared. Right? So if we increase the luminosity by 4 orders of magnitude, that gives you a factor of 100 here. If we decrease the temperature by less than an order of magnitude, let's say by 1/4 in the log, that gives you half an order of magnitude here. So together it's about a factor of 100 times 3 by a factor of 300. So the increase of the radii of the stars can go by quite a lot, and the radii of the stars can increase by a factor between 100 to 1,000 during their evolution. So to give you the perspective, the current radius of the Sun is 600,000 kilometers, which is about 2 light seconds for those who want to think in GR. The distance from the Sun to us is 8 minutes, so it's 240 seconds. No, it's 420 seconds. Sorry. So the Sun will increase the radius to exceed the Sun-Earth orbit. Yeah? And for, say, more massive stars, if we take a 16 solar mass star, we evolved relatively constant luminosity, but we change the temperature by an order of magnitude. Yeah? So from this, we see that we'll increase the radius by more. So the changes in the radii are quite impressive. Now, these diagrams depend on metallicity, and in stellar evolution, the metallicity is the contents of all the elements other than hydrogen and helium. Everything else is a metal. So these are the evolutionary tracks for the solar metallicity, which is 2%. If we go to lower metallicity, which corresponds to either the stars in the halo of our galaxy or in the early universe, when the metallicity was lower in globular clusters, the metallicity is lower in LMC. The metallicity is lower. There are also dwarf galaxies that orbit our system with low metallicity. This evolution looks slightly different, and if you look closely, you may notice that the radius expansion for the low metallicity stars is lower than in the case of the high metallicity stars. And the reason is essentially simple, that metallicity provides a lot of opacity in the atmosphere. If you have lots of opacity, then it's easier to blow up a star, because the atmosphere, the matter in the star, has more of the opacity, and it responds much stronger to higher luminosity that comes from the inside of a star. And this will also have an important impact on the evolution of binaries, because this variation of the behavior of stars with metallicity will affect the evolution in binaries. So these evolutionary tracks are taken from this paper, and I think it would be good if, for you to take this reference, because this reference contains the results of running lots of single evolution codes with various parameters, and then fitting formula that I will try to scare you with, like this. So, of course, I don't expect you to memorize this, but even write it down. But there are codes that have all of these evolutionary tracks written down in terms of approximate formula like that, which allow to trace the evolution of binary components without running in detail the codes that describe the structure and of each component. So now the main sequence time. This is an important thing. This is a complicated formula, but essentially what you should remember is one scaling that I'll write here, is that the time on the main sequence is more or less proportional to mass of the star in the -2 power. So, and for the solar mass, one solar mass, so okay, we can now put it like this. It's about 10 giga-years times m solar over m squared. So for the sun, it's about 10 giga-years, maybe 8. Let's put 8 here to be more precise. And if you go to larger masses, the time on the main sequence, which is, this is one of this crazy formula from Herleitaut and Paul's paper, but the time for the star, oops, where am I here? That the star spends in this first part of the evolution, which is, this is the main sequence, is about 90% of the total time, total lifetime of a star. And during this time, the radius slowly increases, and then the rest, all of this, happens in less than 10% of the time. So then, if you know the scaling, then the time beyond main sequence is about, time beyond main sequence is about 10% of the time on main sequence. So for many binaries, nothing will happen over the first 90% of the time, but certainly once one of the components goes through the main sequence evolution, then there will be quite a lot of things happening really, really rapidly. So I talked about the stellar radii, and here you have the calculation of the stellar radii for two models of the stars. This is a star with the mass of 2.5 solar masses. This is the radius of this logarithm of the radius of the star as a function of time for 3 different metallicities. So you see that this part, the initial part, which is the longest, this is the evolution on the main sequence when the radius of the star increases very slowly, and then you have the 2 episodes. One is when the hydrogen in the core is beginning to be exhausted, then the core core starts to become tighter, and the stars, and at that point the envelope becomes larger. So here you have a very quick increase of the radius. Then we have the ignition of helium, and the star stabilizes for a while, but when the helium reactions stop, then the star expands again, and the radius goes to about 1,000 solar radii, and the exact value is very difficult to ascertain because this is such a rapid process. And the time scales depend slightly on the metallicity, and of course they depend on the on the mass, and but the typical behavior is such that you have a slow increase of the radius on the main sequence, and then a rapid increase, stabilization, and another rapid increase going up again. Now, the stellar winds are another very important ingredient for the evolution of single stars, because we have a very strong mass dependence and metallicity dependence of the amount of wind. For the mass dependence, this is essentially related to the fact that the luminosities of stars are very quickly rising with mass. The luminosity of a star scales its mass to the power 3 to 3.5 over a large number, or a large span of masses. So if you have much higher luminosity, there is much larger radiation pressure, and the amount of wind that is taken out of a star is becoming much larger. And also because of the varying metallicity, metallicity means higher opacity, and higher opacity means that we have a lot more mass loss in the star. So for massive stars that are initially, say, 50, 60 solar masses, at the solar metallicity, you can lose 40 or more solar mass, which is like 60 or more percent of the mass of a star in the wind, and you can essentially strip the star of the entire hydrogen envelope just because of the winds. And they are also important for the evolved stars, for the Wolf-Rayet stars. So let me give you just an update about the evolved stars. There are, I have shown you the diagrams, the evolutionary diagrams for the standard hydrogen and helium stars, but there are also models, and we also have to deal with the helium stars, that is, stars composed only of helium that are completely stripped of hydrogen. So how to get to such stars that are completely stripped of hydrogen? One way to get to them is that we can have an initially massive star that develops a helium core. It has very strong winds, and it gets rid of its hydrogen-helium envelope, and what is left is a naked helium star. Another way is if you have a star in a binary system, it can get into contact with the companion, transfer all the envelope to the companion, and also lose it out in the process of mass transfer, and then you have a binary where you have a helium star and a companion. So there are ways to reach a star that is completely made of helium, and for these stars you can also calculate the evolutionary tracks, because they will keep on evolving, and they don't care about their past that involved hydrogen contamination. They will just evolve as they can, so their evolutionary times are much quicker. The point is that there are two branches here. So you see that for some stars, you evolve mainly on the main sequence, and then you finish the evolution. And probably, for the more massive ones, you can go through a supernova explosion and form a neutron star. If you go to higher masses, what you can see is that they also start entering the giant branch, so they start expanding their radii before they explode as supernova and form either a neutron star or a black hole for the higher, more massive ones. So the helium stars show this dichotomy that for lower masses, they don't really expand their radii up to about 1 1.2 solar masses, but above that mass, they start to expand their radii. They can also become sort of helium giants, and they can, depending on the particular binary that they found themselves in, they can also initiate mass transfers because they will they will be able to fill their Roche lobe. To go to the end of the evolution, we also have to consider the end products of the stellar evolution. These are the compact objects, and the mass and type of the resulting compact object depends very much on the evolutionary scenario, mass, metallicity, winds, maybe rotation. But in general, we believe that for stars up to 8 solar masses in single evolution, we produce white dwarfs. For the stars between 8 and around 20 solar masses, we'll produce neutron stars in single evolutions, and above roughly 20 solar masses, we should form black holes. The exact masses of these neutron stars and the masses of the black holes are subject of quite a debate, and I could produce many graphs like that that show very different dependence of the final mass on the initial mass. Here, final mass for the very low mass stars is going up because this is, on this graph we show the final mass at 12 gigayears, and these stars have just been there and didn't evolve at all, so these are the mass at 12 gigayears is their initial mass. These stars form the white dwarfs, and then we have the neutron stars, and then up there black holes. So for the properties, from the point of view of the binary evolution, if we look at white dwarfs, neutron stars, and black holes, for all practical purpose, neutron stars and black holes can be treated as point-like objects with no radii. And white dwarfs still sometimes can enter, the radius of a white dwarf can play a role in some systems where we have, for example, binary white dwarfs, and which are the progenitors, potential progenitors of supernova 1A, and we can have transfer from the white dwarf, from one white dwarf to another. So probably, this is one of the models of the white dwarf mass radius relation. And essentially, the main thing is that the typical radii of white dwarfs are about in the thousands of kilometers. So a white dwarf is like Earth, and the lower the mass, the higher the radius. So if we have a binary consisting of two white dwarfs that approach one another, the one that will initiate the mass transfer is the less massive one. The less massive one will first is very likely to first fill its Roche lobe and start transferring mass to the more massive one. So it's the poor get the poorer, the rich becomes richer. So it's another example of complete inequality in the universe. Okay, so I think that my time is running out. So I'll just say that for the neutron stars, although for the purpose of my lecture they are point-like objects, you know that they have the radii of about 10 to 15 kilometers, and there is plenty of curves like that you can find in the literature, and probably if only one of them is true, then maybe none of them is true. But we hope to find out in the next years to come which one is true. And for the black holes, they are practically point masses, and the gravitational radius would be 2m in the only good units that we have. So I'll finish this with this slide that shows this is the evolutionary scenario for the single stars. These are the types of stars, and these are the possible mechanism, and these are the possible switches of states of stars when we include the binary evolution. So binary evolution enhances immensely the possibility of switching between various stars, and introduces the possibility to go to these stars like naked helium stars. We can also jump from a white dwarf to a neutron star, even from a neutron star to a black hole if we are lucky with lots of accretion. And in general, binary evolution introduces a lot of phenomenology that is not available in the single star evolution. Thank you.
Come from observations?
Value
you use some 0.02.
0.02 is the solar metallicity.
0.01 you use.
Yeah, well, 0.02 is the reference value. This is the solar metallicity. You know, that's something we can we know best. For say the metallicity of LMC is about 30% of solar. So it's then the metallicity of some globular clusters is about 1% of solar. So the 0.001 is about what 5% of solar.
So is that the lowest one normally uses in these?
No, we use 10 to minus 4 or 10 to minus 5, and also we consider population 3 stars, which are zero metallicity, if you can define zero somehow.
In terms of observations, we have information about the Z dependence of this?
By the small z, lowercase z, meaning redshift. We know that the redshift dependence of the metallicity is not a single valued nice function. There is a distribution of metallicities now, and there was a distribution of metallicities at high redshifts. We see quasars at the redshift of 4, which have a metallicity higher than solar. And we also see galaxies in our neighborhood, or dwarf galaxies, with the metallicity of 30 or 10% of solar. So it's not a single valued nice function, it's a distribution, and there are models for that. So it's not such an easy, nicely defined, nicely measurable thing. You know.